So, good evening to all. My name is Ganeshankar Bhandari and I am a PMR PhD research scholar in IIT Roorkee. And I am here to take the final review session for NPTEL live session for extractive metallurgy taught by Professor Tarun Kumar Kundu from IIT Kharagpur. So, this is the final session for this year's NPTEL course, Extractive Metallurgy. So in this session, we will talk about something different regarding the extractive metallurgy. So in today's world, we are constantly listening the one term that is known as sustainability and the impact of sustainability on mining and extractive metallurgy. So how this sustainability word is going to affect our metal mining and extractive metallurgy, and how to deal with this sustainability, and how to incorporate sustainability and to minimize the environmental impacts of metal mining and the extractive metallurgy in the industrial processes for the recovery of different metals from their particular ores. So in today's lecture, we will talk about the sustainable mining processes and sustainable extractive metallurgy processes, how to incorporate the environment friendly methods in the extractive metallurgy methods, and what are the changes which we have done in last 80 or 90 years for providing the for providing the sustainability during the extractive metallurgy process, and to reduce the environmental burden during this whole extractive metallurgy process for the recovery of different metals. So we will talk about the environmental concerns and sustainable metal extraction processes. So why there is need for sustainable metal extraction? So as we know, that metal extraction has been a backbone of our industrial development, and we can say job creation and transformative economic boost for centuries. However, conventional methods have raised several challenges, like depletion of non-renewable resources. As we all know, these ores or fuels cannot be regenerated. Or if we talk about the fuel, so we generally talked about petrol and coal, and these have taken millions of years to create these fossil fuels, which we are depleting today for our use. So these are non-renewable resources, so we need to recycle them constantly, so that we can avoid the day at which we will left with no metal to extract from anywhere. Then extensive environmental degradation are there, adverse impacts on local communities like displacement of indigenous populations, economic vulnerability due to dependency on a single industry, concerns due to exposure to pollutants, fluctuations in land and property values. So there are several factors which adversely impacts this metal extraction processes. Then there is water contamination, like effluents runoff, acid mine drainage are there. Then air pollution and greenhouse gas emissions are there, which contributes to the global warming processes, which we are talking a lot nowadays. Then there is economic volatility, which is linked to resource-based economies. Like for example, if we take lithium, 10 years ago, the price of lithium was merely around 1,000 or $1,500 per kg of lithium. But nowadays it has shoot up to 10 times, because due to the demand and supply factor, which is working towards this lithium metal, because demand is very high and supply is on very lower level. Because in nowadays we are talking about electric vehicles, and the major element which is used in these electric vehicles for making making batteries is the lithium metal. Then how to attain sustainability in metal extraction? So we can adopt some cleaner or low carbon technologies like biomining or sorting processes. Then we can optimize the resource utilization, then effective waste minimization, recycling and reprocessing are there. So we have to recycle again and again, so that we don't have to mine much, because it will always cost more as compared, in most of the cases it will always cost more uh, economics in extracting the new metals from mines as compared to recycling of metals from the scrap. Then there are stringent environmental regulations and audits, land reclamation to restore habitats and ecosystems, like the mines which has been closed due to the depletion of ore. So we can reclaim those lands and restore them for habitats and for providing proper ecosystems, then addressing societal concerns and resistance. Then coming to the sustainable mining and metal extraction processes, sustainability goal like harness the earth's riches without compromising environment, flora, fauna, and future generations. So emerging technologies like water saving techniques, AI-driven machinery for sustainable mining, and metal extraction waste reduction methods can help for the sustainable mining processes. Then this offer hope in these processes offers hope in reducing the environmental impact and efficient resource utilization. Then waste management involves safely disposing of recycled waste products. Like nowadays, we majorly talk about the e-waste. So these e-waste generally contains around 40 to 50 elements which we are mining from which we can further recycle from these particular e-waste. So recycling is necessary. Then waste management involves safely disposing or recycling waste products. So we have to safely dispose them, or we can recycle them to extract the values back, which can be further reused back for making new products. Then separating toxic substance and ensuring they don't contaminate local ecosystems, and for example, lead acid batteries. So we cannot dispose lead acid batteries like in the drainage, or like we cannot go for landfilling of lead acid batteries. We have to recycle them. We have to ensure that no toxic substance left to be filled in the landfills. Then there is land reclamation, like we can plant the trees on the discarded mines which has been depleted from the ores and nowadays not in the use. Then reintroducing native species or creating safe water bodies which aims to restore the landscape post extraction processes, because any mines generally when we talk about the mining operations, then the operations for a common mine can happen up to 20 to 30 years. After 20 to 30 years time period, the mine will be left behind because we have extracted all the valuable materials from that particular mine. So we can restore that mine by planting trees, and we can reintroduce the native species of that particular area to that reclaimed land, and create safe water bodies, so we can restore the landscape post extraction processes after 30 or 40 years. Then coming to the metal production scenarios and factors on accelerating demand and CO2 emissions. So world metal production, if we see, so highest amount of CO2 emission is done in the aluminium production. Like per metric ton of aluminium produce around 60 million tons of CO2 emission, while copper emit a CO2 value of around something 20 or 25 metric ton. Then iron and steel contributes around 10 metric ton per ton of iron and steel production. If we compare this with the CO2 produced by the world population, all over world population, so that comes to only 5 million or 6 million ton. So if we compare both world population and aluminium production CO2 emission, so it's like 10 times higher CO2 is getting produced during the aluminium production. So how we can solve this problem? As we already know that by a recycling of aluminium, we can reduce the energy demand for aluminium production up to 10 to 20 times. Like for example, if raw aluminium production demands 100 kilojoules of energy per ton of aluminium production, then we can recycle aluminium only with the help of 5 or 6 kilojoule electricity. So recycling is always a better option than going for the inert metal production from their particular ores. So okay, so there are some CO2 emission scenarios and their metal extraction, as we had already talked about. Like nickel produce around 20 tons of CO2 per ton of nickel product, while aluminium produce around 12 to 13 ton of nickel tons of CO2 production per ton of product. Then energy footprints of metal. So every metal whichever we are producing in the industrial processes is creating environmental hazards in the form of CO2 emission, because in most of the processes either we are going with the carbothermal reduction process or we are going with the hydrometallurgical process, but the machineries which are getting used for these uh, metal extraction during the processing itself steps are using high amount of energy, and that energy generally comes from the burning of coal or other fossil fuels or sometimes hydro plants. However, most of the energy is coming from the burning of fossil fuels. So these fossil fuels create the CO2 emission and it increase the global warming in the processing steps. So if we talk about sustainability, so recycling is the best option for the sustainability. So if we talk about the global estimates of end of life recycling rates for 60 metals and metalloids, so most of them are on lower than 1%. Most of the metals we are not at all recycling, like lithium, beryllium, vanadium, they are going to the landfills. For example, the fresh example, hot topic is lithium ion batteries recycling. So we are generating around around 4 to 5 million tons of lithium ion batteries per year, discarded lithium ion batteries per year, but we are able to recycle only 1% of them, only 4 to 5% of those discarded lithium ion batteries to recycle the lithium back, so that we can reuse that lithium to make new batteries. Most of the lithium which we are using in the production of new lithium ion batteries is coming from the mining of raw material from Chile or Australia, and it is getting processed in China. So there is huge possibilities for the recycling in the lithium, or we can recycle. Apart from lithium, we can recycle nickel, cobalt, and manganese values from these discarded lithium ion batteries, which can help to reduce the carbon footprints for the battery making and tends to more sustainability in the extractive metallurgy. While most of the rare earths we are recycling only less than 1% of most of the rare earth metals from lanthanide series. And nowadays, if we talk about the use of rare earths, so there is huge use of rare earths. Every electric components which we are using nowadays is made up of with the help of these rare earths materials, from chip to laptop to semiconductor devices. Every electronic material is using these rare earths, and these for fulfilling the demand and supply of these particular rare earths to make electronic components is coming from the raw material mining. We are not talking about recycling at all. However, major values are lying in the in the discarded products, discarded e-waste products, which can be recycled back for the recovery of these rare earth metals, so that we can reuse them in the uh, making of new products. Okay, so okay, so there. Now coming to the steel making process. In India, if we talk about India only, then we produce around 150 million tons of steel every year, and we are targeting 300 million tons of steel production by 2030. However, this steel production comes with a lot of CO2 emissions, which contributes to the global warming process. And as we are talking about the net zero carbon emissions by 2070 or 2060, so we have to we have to incorporate some changes during our steel making process, so that we can make it sustainable and net zero carbon emission process. For evaluating the sustainability of the feasible processes, combinations, raw materials, reductants, and aggregate, it says the origin and degree of sustainability of the underlying electrical energy are essential, because we are using a lot of electrical energy, and this electrical major part of this electrical energy is coming from the burning of the fossil fuels. So by incorporating the electrical energy which is coming from the renewable resources like wind energy or solar energy, we can uh, step towards the sustainable steel making processes, so we can reduce the carbon footprints up to some extent during the steel production processes. So the entire electrification of the metallurgical sector will make the system more sustainable if the electrical energy needed for the process steps and also for the production of non-fossil reductants is renewable and fossil free. So we have to think in that term. However, some major part is also coming from the blast furnace during the steel making processes, because we are using fossil carbon or coke as a reductant, which is generating CO2 CO2 gas in very high amounts. So we have to think about that scenario also, how we can decrease the coke rate and how to increase the hydrogen purging during the steel making processes, so we can go towards more sustainable steel making processes, and we can reduce the carbon footprints. However, the major challenge is there, how to produce cheap hydrogen gas with the help of these renewable renewable resources, because most of the hydrogen production is also depends on the biomass or like photo like decomposition of water during electrolysis process, and this electrolysis process of water needs very high amount of electrical energy, and as we had already talked about, this electrical energy is coming from the burning of fossil fuel. So it's like a cycle. We are going for the hydrogen reduction processes during steel making processes. However, that hydrogen produced which is getting used in during these processes is getting generated with the help of the electrical energy, and that electrical energy is coming from the burning of fossil fuel itself. So we are again back to the CO2 net CO2 emission will be very high during this during this whole steel making process. So we have to think about a process so that we can use these renewable the electricity generated from the renewable resources to generate the hydrogen and to incorporate this hydrogen gas during the steel making processes, so we can go towards more sustainable steel making processes. Okay. Then coming to the sustainable aluminium production, as we had already talked about, aluminium produce very large amount of CO2 emission per ton of CO2 production. However, with the help of the recycling of aluminium products which are getting scrapped every year, we can reduce the carbon footprints during the aluminium production processes, and we can incorporate, as we all know that aluminium is produced with the help of the molten salt electrolysis process via Hall Herold cell, and these Hall Herold cell use very high amount of energies, and this energy is coming from the burning of fossil fuels. So we have to incorporate the energy from the renewable resources so that we can decrease the carbon footprints of the aluminium production. So there are two different ways. One way is to reduce the carbon footprints via using energy from renewable resources, and another way is recycling the aluminium scrap so that we can decrease the energy consumption during the aluminium production processes. And in then coming guys, metal requirements for a low carbon transition in the transportation and electricity sector. So there are some, okay, then conflict of sustainable tech. So sustainable metallurgy, holistic and systematic approach of producing metals that balances engineering, like foundation and innovation of whole extractive metallurgical processes, because we cannot change the foundation and foundation of whole extractive metallurgy processes in a night. So we have to think about those things also. Then economic viability of the processes, and with the efficiency we have also have to see the efficiency of the processes. Then social fairness has to be there. Then coming to the environmental sustainability, so this is a holistic and systematic approach of these all things, and we have to incorporate all the changes for making the extractive metallurgical processes more sustainable. and the beginnings can be from the use of whatever the electricity we are going to use during these extractive metallurgical processes. We can incorporate the electricity generation from the renewable resources like windmill or solar energy. So we can incorporate those changes so that we can reduce some CO2 emissions like 5 or 10%. We can reduce up to some extent the CO2 production during the whole processing steps. Then there has been some new developments has been done in metal extraction processes, so that we can go for the more sustainable extractive metallurgical processes, like there one process is there which is known as solvometallurgy, which is an emerging method for the metal extraction. So solvometallurgy is known as the net zero waste processes for extraction of metals from ores or industrial residues, scraps or waste, which uses non-aqueous solvents for the extraction of the particular elements from their ores. Uh, what are the advantages of this solvometallurgical processes? So, limited water consumption is there, and wastewater generation will be negligible. Then, combined single-step leaching and solvent extraction process simplified the whole hydrometallurgical processes. Then, more selective leaching in solvent, leading to less acid consumption and purification steps. Then no silica gel formation in silica rich ores. So there are several advantages which can be incorporated by the use of solvometallurgy for the extraction of metals from their particular ores. Although this solvometallurgy is a part of the hydrometallurgical operations. First, we have to dissolve the metals in some liquid solvents. Then we can go with the solvometallurgical processes, or we can go with the ionic liquids, which are more greener as compared to the inorganic and other acids which are generally used in the industrial processes for the recovery of metals. The selection of best solvent for a solvometallurgical process is based on performance, stability, recyclability, cost, environmental impact, volatility, flammability, safety. So there are numerous factors on which we can select the best solvent for a solvometallurgical process. Like common example are methane sulfonic acid, uh, or we can go for gas to liquid solvents, which are isoparaffins or normal paraffins are green organic solvents, but they tend to degrade over time. So we have to keep that factor in mind also, because if they are going to degrade over time, so the recycling of these solutions will become costlier, or we can say the recycling of these solutions will not be possible, so it will add to the whole overall economy of the extraction processes. So the extraction processes will become more and more costlier. Then there are some inorganic solvents like liquid ammonia, liquid sulfur dioxide, anhydrous hydrogen fluoride, thionyl chloride, sulfuryl chloride, phosphoryl chloride, dinitrogen tetroxide, and antimony trichloride. These are very reactive in nature, and very dangerous and toxic, so we cannot use them. Then there are some supercritical fluids like supercritical CO2 with TBP and HNO3, and supercritical CO2 with fluorinated diketones as solvents for direct solid leaching processes, which can be functionalized at room temperature. Functionalized room temperature ionic liquids are there. Then some deep eutectic solvents are there, which are promising and tunable alternatives for the existing inorganic acid processes. But however, the cost of these as of now, the cost of these solvents are very high, so it will not be easy to go for a economical extraction processes for the recovery of metals from particular ores. Then coming to the varieties of these particular solvents, some are there like room temperature ionic liquids are there. So ionic liquids are solvents that only contain single charge cation and anion, and these charges are often delocalized. One or more alkyl chain attached to the cation and lower electrostatic interactions than in simpler inorganic salts lower the melting points of IELs. So IELs have an extremely low vapor pressure, virtually non-volatile, and thus considered as green solvents, more safe and environmentally friendly than conventional molecular organic solvents, which tends to evaporate uh, with time. So these are considered more greener and more safer option, or we can say more economical option as compared to the molecular organic solvents like citric acid or acetone or ethanols, those. Then due to electrochemical stability in combination with an intrinsic electrical conductivity, IELs are ideal electrolytes in the electrowinning and electrorefining processes of metals, which includes reactive metal that cannot be processed in aqueous solutions like sodium or uh, potassium. So these are reactive metals which cannot be processed in aqueous solution. However, with the help of IELs, we can process those metals easily. Then IELs are also attractive as alternatives to the organic phase in solvent extraction and as a replacement for the aqueous phase in leaching process. So main limitations of in ionic liquids are like high viscosity, limited chemical stability, and these are difficult to recycling and high cost, etc. So there are some limitations also which needs to be reworked for for incorporating the use of these ionic liquids in the solvometallurgical operations, or we can say to make solvometallurgical operations more economical as compared to the inorganic acids which we are using nowadays. So these are very high, these are having very high cost and viscosity is very high, so the filtration process after the after dissolution will be a bit difficult. Then chemical stability is limited, and these are difficult to recycle back. So these are some disadvantages which needs to be reworked. Then coming to the ionometallurgy, like ionic liquids and deep eutectic solvents for special purposes. These neoteric solvents are studies for the recovery of valuable metals from end-of-life lithium-ion batteries, e-waste, magnets, and phosphorus, etc. So nowadays, researchers are working on these types of these ionic liquids and deep eutectic solvents for the recycling of metals from the e-waste, which is bit difficult as compared to the particular ore, as we can say. For example, when we talk about the printed circuit boards. Then a single printed circuit board contains around more than uh, 20 to 25 elements which are present in the periodic table and which needs to be recycled back for proper economical purpose and to or we can say for sustainable metallurgical operations. These 25 elements needs to be recycled back, and for selectively recover these 25 elements, we have to go for ionic solvents or deep eutectic solvents which are having selective nature, or we can say after leaching of these elements we can go for solvent extraction processes for the selective recovery of these particular elements from the those particular e-waste. So another trend is applying these solvents to recover the metals from low-grade metal-containing materials like red mud, or which is basically a bauxite residue, then jarosite and goethite from the zinc industry, etc. So in the ionic liquids are too expensive for general use. Cheaper ionic liquids like solvents like deep eutectic solvents has been developed. Deep eutectic solvents are composed of an ionic hydrogen bond acceptor, which is generally choline chloride, and a molecular hydrogen bond donor that can be urea, ethylene glycol, or citric acid, or formic acid, or oxalic acid, depending on the requirement. The resulting mixture has a much lower melting point than its component and is usually a liquid at a room temperature. Basically, these choline chlorides, and if you talk about the choline chloride and urea or ethylene glycol or citric acid, so at room temperature, these are basically powder. These are basically in the solid forms. But when we are going to mix them in a predefined proportion, so due to the eutectic points of these particular mixtures, this particular mixture is going to attain a liquid form at room temperatures, and in the liquid form we can easily go for the leaching processes with the help of these deep eutectic solvents. So we are talking about the we are working on the eutectic points. That's why these solids mixtures are known as deep eutectic solvents. So one part of the mixture will be hydrogen bond acceptor, which is majorly choline chloride, and one will be the hydrogen bond donor, which can be from the urea, ethylene glycol, or citric acid, or oxalic acid, or formic acid, etc. Then coming to the supercritical fluids technologies for metal recovery. So supercritical fluid, it's like it is a condition, or we can say it is a particular point at which a liquid or gas behaves like a supercritical fluid, or we can say it possesses all of the three states: gas, solid, and gas, plasma, and liquid. So this point is known as the critical point. This point is known as the critical point, or we can say supercritical point for a particular fluid. So at for example, at supercritical point, CO2 can act. CO2, which is which is basically having gaseous form at room temperature, can act as a fluid medium at room temperature itself. So supercritical fluid is a kind of fluid whose temperature and pressure are higher than its critical states. So viscosity, density, diffusion coefficient, solvation capacity, and other properties of SCF are very sensitive to the changes in temperature and pressure. Like supercritical water, water can achieve a supercritical condition at a temperature of around 374.15 degrees Celsius and at a at a pressure of 22 megapascal, and it will be having a specific gravity of 0.322 instead of 1.0 at 1 atm condition, at 1 atm, or we can say atmospheric conditions. While supercritical carbon dioxide is having a can be achieved at a temperature of 31 degrees Celsius, which is basically a room temperature, at a pressurized condition of 7.4 megapascal around, and it will be having a specific gravity of around 0.448. And these are sustainable green solvents as well as highly promising reaction mediums, uh, because during the supercritical conditions, the solubility limit of these fluids increase many-fold. So water can act as a very good medium for solvometallurgy at their supercritical conditions. For example, we cannot expect we cannot expect any metal oxide dissolution in water at normal conditions. However, at supercritical conditions, the water can dissolve the metal oxides some metal oxide easily at supercritical conditions. Same can be said for the carbon dioxide. Basically, at room temperature, it is in the form majorly. It is basically in the form of gases. However, if we are going to increase the pressure at room temperature also, then it is going to attain the supercritical fluid condition, and it can act as a uh, solvent for the organic phases. Then however, the viscosity will be very lower for the supercritical fluids, and high diffusivity of solutes in supercritical fluids combined with very high reactivity, which can produce excellent mass transfer characteristics. Significant progress has been made in the detoxification of e-waste, recovery of metal ions, and removal of refractory polymers by this supercritical fluid technology. For example, supercritical CO2 can be used for the extraction of hazardous electrolytes from the discarded lithium ion batteries, which otherwise has to be go in the landfills, and these hazardous electrolyte contains LiPF6 as a material which can break into hazardous hydrofluoric acid by coming into the coming with the contact in water, and can create can create major problems during the landfilling processes. Or we can dissolve the polymeric fraction of the discarded printer circuit boards with the help of this supercritical CO2 process. Then metal extraction by supercritical CO2 formed from solid metric include the formation of complex anions in the solid supercritical fluid interface, anion exchange, and the mass transfer of ion association complexes into supercritical fluid phases. Then coming to the metal recovery from e-waste by supercritical fluid technologies. So some base metals can be recovered from these supercritical fluid technologies, like from waste PCBs, supercritical waste system, SCW system at a temperature of 400 degrees Celsius. Supercritical water system has been applied for the recovery of the copper metal at a temperature of around 400 degrees Celsius with a pressure of 30 megapascal, and within 2 hours we can extract around 98.11% of copper from these waste printed circuit boards. While supercritical water system plus leaching process at around 420 degrees Celsius for a time period of 60 minutes, and after followed by the leaching with HCl and H2O2 can recover 99.8% of copper and 80% lead from these printed circuit boards. One another research has reported a supercritical water system plus electrokinetic processes at around 440 degrees Celsius with a pressure of around 25 megapascal, uh, followed by H2O2 leaching process in PVP, uh, recovered around 95% of 99% of CO2 in the nanoparticle forms. While supercritical water system at around 350 degrees Celsius and chlorination process can recover 95% of cobalt and 98% of lithium from discarded lithium cobalt oxide batteries. So then coming to the precious metals recoveries from these waste PCBs, some researchers have recovered gold, silver, palladium, and tantalum via supercritical water system at a temperature of around 400 degrees Celsius and a pressure range of around 20 to 30 megapascal. With the help of this supercritical water system, they have recovered major amount of precious metals present in the waste PCB boards or waste tantalum capacitors. Then coming to the glass transformation, waste PCBs can be transformed to the glass also with the help of this supercritical water system at a temperature of around 400 degrees Celsius for a time period of around 40 minutes. And additives are NaOH, some H2O2 we have to add, and that can convert the polymeric fraction, or we can say silicon SiO2 fraction present in these waste PCBs into the glass, which is anorthite or albite glass. However, there are some limitations in these supercritical fluid exfoliation processes, like high equipment investment and operating costs are very high, then require further research in technical solutions. The challenges like corrosion and salt precipitations have mostly been overcome. Then supercritical fluid technology can remove hazardous components and recover valuable materials simultaneously without creating any secondary pollutions. If we talk about the supercritical carbon exfoliation, carbon fluid process, so as soon as we are going to introduce this supercritical carbon to the atmosphere, that is again going to get converted into the CO2 gas, while leaving behind the elements or the solvents or whatever the elements it has dissolved inside, leaving behind as a residue material, and CO2 will be released back in the environment. So there is no secondary pollution can be created during this uh, supercritical processes by using water or by using CO2 gas. Then plants for metallurgy like phyto mining or phyto, there are some other processes also which are based on the plants, which use plants for the metallurgical operations, like these processes are generally known as phyto mining or phyto extraction or phyto remediation processes. So phyto mining is defined as a process of using hyper accumulator, or we can say enhanced ability to tolerate and accumulate metals, accumulator plants which are capable of bio extracting metals from soil in order to explore them economically. So as we all know, the roots of plant extract the required minerals from the soil for their own use. Like when we say food consists iron, which are helpful for the human health. So these are coming from the plants, and plants is extracting these iron particles from their roots via soil. So that process for in so some researchers are working to enhance, or we can say to speed up these plant the ability of the plants to extract minerals from the soil. So these processes are generally known as the phytomining. However, as of now, these are not at all economical in nature, but researchers are working, or they are looking for the prospects of phytomining processes to recover metals from the soil, or we can say from ore, with the help of the plants. So phytomining is an environmentally friendly and economically viable solution that addresses the growing demands for metal resources while simultaneously contributing to energy production by harnessing the biomass. The accumulation of metals in plants occur in their root system or in the aerial biomass like stems, leaves, and flowers. So phytoremediation is the process of remediating or cleaning up a soil elevated with pollutants by the use of plants. The phytoextraction is the process of using hyperaccumulator plants to absorb valuable inorganic elements from soil in a natural or in an induced manner for the specific purposes like pharmaceutical, aromatic, energy, biochar, etc. or profit after valorizing the produced biomass. Then the bioaccumulation factor like BAF is the ratio of metal concentration in the aerial plants of a plant to that in the surrounding soil, and translocation factor is known as ratio of metal concentration in the aerial plants parts to that in the roots, which are used to determine the efficiency of metal uptake from soil to plant and metal translocation within the plant respectively. So these processes are some industries are using these phytomining and phytoextraction, or we can say phytoremediation processes for the extraction of metals from the plants. However, these are limited to the pharmaceutical companies because they are not extracting the purest form of metals from these plants. They are relying on the particular elements in those particular plants for making the medicines. So in that case, it is working economically. But however, if we are expecting to speed it up for the industrial metal production, so it will not be possible at a huge scale because we will not be able to recover that much amount of metal with the help of these phytomining or phyto extraction processes. So there is an established threshold which is metal for a hyper accumulator, like how much amount of milligram per kg of dry plant can absorb. A plant, how much amount of milligram per kg a plant can absorb. So there is a limitation. So obviously we cannot use this for the metallurgical operations, for huge operations like steel making. We cannot expect to recover steel with the help of this with the help of these phytomining processes. However, in the case of pharmaceutical operations, we can rely on these phytomining operations because we need some ppm level of elements, particular elements in sometimes in starch, on some in some food material. So we can rely on that things, making the soil in the vicinity of the plant's roots more acidic and releasing organic compounds are the plant's mechanism to absorb metals. So as we can see in this graph, so there are some threshold limits for particular elements via hyperaccumulation via phytomining processes, like it can consist up to 1 milligram per kg of silver or 1 milligram per kg of gold. Then cadmium can be up to 100 milligram. However, manganese can be up to 10,000, or zinc can be up to 3,000 milligram per kg of material. And number of hyper accumulators plant species are like 24, 29. So there are number of plant species which are acting as a hyper accumulator for the phytomining operations for particular elements. Like for nickel operations, nickel, there are around 532 plant species which can act as a hyper accumulator for the recovery of nickel from the soil via phytomining processes. But obviously, these recovery processes are limited to the pharmaceutical operations only. Then there are biotechnologies for metal recovery operation, or we can say bio-leaching operations, which use bacterial leaching processes. So in the bio-leaching of sulfidic ores, reductive dissolution of oxide ores, metals are released into aqueous solution by solubilization process. Bioabsorption, bioaccumulation, bioprecipitation, and bioreduction enrich the dissolved metals of leached streams or diffuse metals of wastewater as precipitate. So in these processes, as the name suggests, biotechnology. So we are using different types of microorganisms for expediting the precipitation or dissolution, or we can say extraction processes of the particular metals from the ores. We can go for the bio leaching processes. The common example for bio leaching processes is the recovery of copper metal from the low grade copper sulfate ores. And it is industrially some industries are also using this bio metallurgical operations for the some industries, if I am not wrong, some industries in Finland and Switzerland are using these bio leaching processes for the recovery of copper from the heap leaching via the heap leaching process of very lean grade copper ore, which consists around 0.2 or 0.3% copper. So they are using these techniques for the recovery of copper metals from the lean grade copper sulfate ores. However, some research is needed to explore. Some more research are needed to explore novel microorganisms which can thrive in complex physiochemical conditions of waste streams and concentrate with diffuse critical metals. Then there are some major challenges for metal recovery, like lower concentration of critical metals, low pH values, coexisting metals and salts. So there are selectivity is on the low for in easy manner we can say selectivity of the metal is on lower level. So we have to some research are required to work on that, so that these operations can be industrially exploited for more and more metal extractions from their particular source. Okay, so this is okay. Then there are some biosurfactants which are used as collector and frother in froth flotation processes also. So froth flotation process we have talked about during the mineral beneficiation processes in first or second week lectures, when we were talking about the various mineral processing operations for the for concentrating the lean grade ores into the particular concentrates. So we can go so these those particular concentrates can be used in the further extractive metallurgical operations. So some research are going on to use these biosurfactants as collector or frother material during the froth flotation operation. Then some research are working on membranes for metal extraction or separation. So these membrane requirements are if we for example, these membrane are required for the recovery of metals from the leach solutions, or we can say from the sea water. When we talk about the magnesium, when we talk about the recovery of magnesium or sodium or calcium from the sea water, so we require these membranes for the recovery of those metals. Or we can some research are going on for the recovery of for the use of these particular membranes, so that we can selectively recover the elements from the least solution, its least solutions also. Then there is electrodialysis process. Okay, so now coming. Okay, So now coming to some metal mining, environmental impacts of mining and metal production. So there are numerous environmental impacts of the mining industry on the environments, like water management, land use management, air pollution, greenhouse gas emissions, and radiation exposure. So in this week, we will majorly focus on We will majorly focus on the greenhouse gases management during the metal mining processes. So various environmental impacts of metal mining involves physical disturbance to the landscapes during the exploration or overburden removal or drilling, etc. So when we are, for example, when we are going for a mining, let's say in an area of 2 acres. So it is not like that we are only acquiring that, we are only disturbing that 2 acres of land for mining. The surrounding, for example, the surrounding lands of at least 5 to 6 acre radius will get disturbed due to this exploration, or we can say mining operation, because we are going to require some more land for keeping the overburden of to develop that particular mine site. And due to the noise pollution and air pollution created by that particular mining operation, the surroundings 5 to 6 acres radius of land is going to get disturbed, or we can say there will be the hazardous environmental impacts of that particular mining operation. Then coming to the air pollution, like from drilling or blasting, there will be from during the drilling or blasting, some particles will get dissolved in the air. Then during the metal processing cycles, like CO2 emission will be there. So there will be lot of air pollution in the surroundings of that particular mining area. Then coming to the water pollution, water pollution will be majorly created by leaching operation, smelting operation, solid waste disposal operations. So water pollution will be there. Then there will be gas emission in the form of CO2 emission, and there can be radiation exposure also if we are talking about uranium or some radioactive metal mining process. Then several human health issues will be there in the nearby living areas. So if we talk about the hazardous pollutants during the mining processes, so major hazardous pollutants involve like dyes or pharmaceutical and personal care products, which then there are heavy metal ions and fertilizers and pesticides. Then the effects of these pollutants are like on plants, so danger. It is very dangerous for the plant growth and affect photosynthesis processes or decrease soil quality, and cell due to that cell death will be there, which will hamper the plant growth in the long run. Then animals are also going to be get affected during these mining operations, like dangers to aquatic animals. Few pollutants are carcinogenic in nature or mutagenic to animals. Then loss of biodiversity will be there in that diameter of around 10 to 12 acres of land. There will be loss of biodiversity. Then if we come to human beings, effect on human beings, then if there are some carcinogenic pollutants are there, then it can create the cancer in human beings. Then mental retardation will be there, damage to nervous system, and due to the noise pollution, the ears can get affected. Then there are environmental uh, effect, like increases in toxicity levels, then increases COD and BOD, and effluents will affect the whole environmental surroundings of the mining operations. So coming to the greenhouse gas emission process, uh, when we are talking about the sustainability, so we have to keep in mind during the sustainability, environmental factors like natural resources use, environmental management, pollutions and preventions. Then there are some social factors like standards of living, education, community, equal opportunity, then economic, like profit, cost saving, economic growth, research and development. So when we are talking about sustainability, so it is a mixture of all three. Okay. we cannot leave one of them behind, like we cannot leave environmental factors behind, and we can only focus on, while focusing only on social or economics, or we can not only focus on economics while leaving behind environmental or social. Then coming to the greenhouse gas emission and their remedies, like mining industry generate around between 1.9 to 5.1 gigatons of CO2 equivalent per year of gigahertz gas emissions annually. The majority of emission in this sector originate from fugitive coal-based methane that is released during the coal mining operations, which generates around 1.5 to 4 gigatons of CO2 production. Mainly at underground operations, our power consumption in the mining industry contributes around 0.4 to 0.4 gigatons of CO2 emissions. So, as we can, as we are seeing, the coal bed methane is generating a huge factor during the mining operation, which is coming during, which is generating during the coal mining operation. So the remedy can be simple. We can try to capture that CH4 which is generating from these coal beds during the coal mining operations, and if we are able to capture this CH4, so that can be a win-win situation. Like we are able to reduce the CH4 emission in the environment, which will further contribute to the greenhouse gas emissions. And by capturing this CO2, by capturing this CH4 gas, we can use this CH4 gas as a fuel source in the industrial processes, in the extractive metallurgy industrial processes itself, or we can uh, use this CH4 gas as a fuel source in the other things also. So that will be the win-win situation for the mining industries. Then greenhouse gas emissions in mining, metals and recycling can be lowered by the following routes. Like we can go for decarbonization processes by using hydrogen during the reduction processes, and as a fuel source we can use hydrogen. So and for example, when we are burning the hydrogen as a fuel source, so the byproduct will be the H2O instead of the CO2 when we are working with the carbon as a fuel source. So CO2 as a byproduct is not at all contributing in the greenhouse gas emissions. So we can use hydrogen as a reductant source, or we can use hydrogen as a fuel source also. Then we can use renewable resources like biomass as the alternative to the coal processing in the industrial metallurgical operations. Then carbon capture and storage, or usage of CCU should be there in the metallurgical operations via CO2 sequestration process. So coming to the use of hydrogen, some industries are using hydrogen as a reductant source instead of going with the carbon as a reductant. So it is also helpful because with the use of hydrogen as a reductant or we can say as a fuel source can contribute to the faster kinetics for the reduction processes for any metals, because with the help of hydrogen the reduction process is gas to solid reaction, while if we are talking about with the reduction with the help of carbon, so it is majorly solid to solid reaction. Or first we have to burn that carbon to produce the CO gas, which will further contribute in the reduction processes as a CO carbon monoxide gas, so that we can reduce the particular metal. So in if we talk about the hydrogen as a reductant, so some many research are going on which are on the laboratory scale, like we are going with the hydrogen reduction of lead oxide, zinc, copper oxide, titanium oxide, Cr2O3, MnO2, rare earth oxides, then germanium oxide, SnO2, and other miscellaneous oxides like B2O5, Nb2O5, CuO2, CO2, U3O8, ZrO2, Y2O3, and thorium oxide. However, they are, these research are only on the in the laboratory scale. Uh, the reduction processes of these oxides are not industrially applicable yet. Researchers are working on making them viable for the industrial for the further industrial operations. But there are some oxide reduction processes via hydrogen reduction that are using in the industrially, or we can say that are in commercially applied in the industry. Like they are going for the production of tungsten from the tungsten oxide, and they are also going for the production of molybdenum, nickel, and cobalt metal from from their respective metal oxides via hydrogen reduction processes industrially. And applications for advanced material processes other than metal productions are also there. Like they are using hydrogen in the sensor applications, doping treatment for semiconductor hydrogenation, for photocatalyst materials, addition for microelectronic components, and usage in plasma applications. Then commercial metal productions using hydrogen. So they are producing tungsten. The raw material is WO3, and method or equipment which they are using in solid state reduction in rotary kiln. And they are producing pure tungsten grade powder, which can be further used for the further applications. Then they are going with the production of molybdenum via with the molybdenum metal powder with the help of MOO3, H2O MOO3 hydrogen reduction processes in the form of solid state reduction in various furnaces such as Pochar furnace, rotary kiln, walking beam furnace, and fluidized bed reactor. Then for the nickel production, they are using nickel sulfate complex as a raw material, and they are going with the pressure leaching process in autoclave. Uh, then and then after that, carbon is followed by the hydrogen reduction process for the production of pure nickel powder. Then coming to the cobalt, they are using cobalt pentamine complex as a raw material, and they are also going with the pressure leaching process in an autoclave. The process is industrially used by Sarit Gordon and Outokumpu, uh, and this process is also followed by the hydrogen reduction process for the production of pure metallic cobalt. Then coming to the carbon sequestration process, which can be applied during the mining processes uh, for reducing the carbon footprints of the mining processes. So when we talk about the kilotons of CO2 equivalent produced by every country, so China is on the top. They are producing around 13 million tons of CO2 equivalent per 13 tons of CO2 equivalent. Then United States and India is lying on the fourth number. So for as we already know, according to the Paris agreements for net zero carbon emission, we have to achieve a net zero carbon emission status by 2070. And to achieve that net zero carbon emission, we have to uh, adapt lot of new things in the mining industries also, and extractive metallurgical processes also. So carbon sequestration process is from one of them. So captured CO2 can be used in various processes. So when we talk about the mineral industry, so captured CO2 can be used in the mineral industry to make different carbonates via mineralization processes. So the common reaction is like calcium oxide can be converted into calcium carbonate with the, by capturing CO2 from the atmosphere or from whatever source we are trying to capture the CO2 from. Then we can and we talk about extractive metallurgy, then we can enhance the fuel recovery processes also. We can use the different types of fuels like oil or gas, or we can use uh, natural gases as gas or hydrogen gas as a fuel source, so that we can incorporate during the extractive metallurgy and mining operations. Then coming to the carbon sequestration by mineral. So mineral carbonation is presumably a safer alternative to the other geological sequestration. Carbon is carbon is immobilized into stable carbonates as rocks. So with the help of mining processes itself, we can go for the carbon sequestration processes, like with the help of, for example, calcium carbonate rocks. We can convert some metal oxide rocks with the help of carbon sequestration into metal carbonates rocks, which are not useful for further extractive metallurgical operations. So this process can safely sequester 36,000 billion ton of CO2, which far exceeds the sequestration potential of geological reservoirs. Like metal oxide plus CO2 can get converted into metal carbonates while generating the heat. Approximately 2 to 6 gigatons of mine tailings and ore burden exist worldwide, which can sequestrate around 20 to 60 million tons of tailings and ore burden are being produced every year, with 190 to 332 million tons of sequestration potential for the carbon. So we can use those mine tailings, mine burdens, and the tailings produced during the various extractive metallurgical or mineral processing processes, which can sequestrate around 190 to 332 million tons of sequestration for carbon, and that is around, we can say, 5 to 10% of the whole CO2 which is produced during the whole mining or extractive metallurgical operations. Then coming to the mine waste, which has no economic values, and it can be reused for CO2 sequestration, would enhance its economic performance. Like mineral carbonation is of two types. For example, in mine waste, we can use red mud for CO2 sequestration process, uh, which can sequestrate CO2 for converting uh, high. The major advantage of that particular process will be like the red mud generally having a pH value of around 12 to 13. That is very highly basic content, and we cannot discard that like that. So with the help of CO2 sequestration, we can lower down the pH value of the red mud up to 7 to 8, which is almost to equivalent to the neutral conditions, and that it can be discarded, or we can go for the landfilling processes. So it is a win-win situation. One, we are sequestrating CO2 gas inside that red mud material, and at the same time we are decreasing the pH value, highly basic pH value, to the neutral content. So it will not be going to be having very major impacts on the environmental. Uh, it is not going to have major environmental burdens during the landfill operations of that particular red mud material. Then coming to the mineral carbonation is of two types. First one is direct, which is in situ, and indirect, which is ex situ. Then direct mineral carbonation has been reported for the capture of CO2 from the atmosphere, which is using materials such as olivine and serpentine. Olivine forms around 60 to 80% of the Earth's upper mantle, which in turns comprises around about one fourth of the Earth. Mining waste enriched in Ca2 plus Mg2 plus Ca2 plus and Mg2 plus dissolves and forms carbonates upon reaction with atmospheric CO2, converting them into MgCO3 and CaCO3, and that are just rocks, and those rocks can be reused for making ceramic materials. So it is a win-win situation. So during the mining activities, whatever CO2 is getting produced during the ore extraction and beneficiation process, it is going into the atmosphere, and then from atmosphere the mine waste, this mine waste is recapturing this CO2. So it is whole cycle, whatever the CO2 which is getting produced during the mining activities can be reabsorbed back by the mining waste. However, the process, if we are talking about natural sequestration process, it can take several years. So it is very slow process. So we can do we can apply some processes to enhance this reactivity so that sequestration process can enhance, and the years of time can get reduced to the months or maybe into the days. Then there are some factors which affect carbon sequestration process in the mining operations, like grain size of the mining waste into also significantly influence mineral carbonization, area and reactivity. Fine grain tailings store more CO2 and are more reactive as compared to the waste rock. So lesser the size, more will be the surface area, and more will be the higher will be the reaction kinetics. Then an increase in the temperature of mining waste from 10 to 40 degrees Celsius can also increase carbon sequestration by a factor of 10. So as we had already discussed, there are some factors which can use to enhance the carbon sequestration process for the mine waste or ore burdens. The sequestration of CO2 depends on the weathering intensity of the mining waste. Then there are some advantages of minerals carbon sequestration, like carbonation of MgO could capture 2 to 3 gigatons of CO2 per year from the atmosphere and make a sustainable contribution to mitigating climate change. On the other hand, this MgO is going to get converted into the MgCO3, which is basically magnesium carbonate, and that magnesium carbonate can have various applications in the ceramic industries. So it's a win-win situation. On one hand, we are capturing the carbon from the atmosphere, and the MgCO3 produced during this carbon sequestration process can be reused back for making useful products. Then spontaneous reactions, which can make the reaction proceed with a relatively small amount of energy. The product is more stable other than CCU technology applications and has many industrial applications. As we had already talked, the product created during this carbonation method is generally metal carbonates, and these particular metal carbonates can be used in the ceramic industries for making refractory materials or in some other applications. Then product obtains has a wide range of applications. Process can also occur in simulated conditions and mainly have applications in the cement industries. So there is generation from power plants or industrial operations. CO2 is getting generated, and with the help of mineral carbonation plants, we can expedite the process of this carbon sequestration, and from expediting the process, we can create the valuable metals in the form of mineral carbonates, and that can be reused back. That can be reused as a construction material, or can go back to the mining operation and can be disposed of. Then there are some industries which are using carbon sequestration processes by minerals, like Carbon 8 Aggregates Limited, which is targeting thermal waste materials, and carbon product, final product which is getting generated is carbon 8 aggregates. And this carbon 8 aggregate has applications in blocks, precast concrete, ready mix concrete, or screed. Then there is Solidia Technologies, which is targeting the cement industries for carbon sequestration processes. They are sequestering the CO2 gas produced during the cement making operations. So they are targeting that particular CO2, these particular CO2 processes. And the final products is Solidia Cement and Solidia Concretes, and applications are construction materials. Then Kajma Corporations, the Chugoku Electrical Power Company and Denka Company Limited, their target materials are concrete materials and cold fly assays. And the final products are CO2 storage under infrastructure by concrete materials like CO2 SUI COM. Then applications are concrete curbs, fence blocks, and precast concretes can be made with the help of these products. Then Carbon Cure Technologies Limited is targeting the ready mix concrete and concrete machineries, and the final product is enhanced concretes, and applications are construction industries. Then coming to the biohydrometallurgical operations, so there is ore, we have to reduce the size, then physical concentration will be there, and after that physical concentration we can go for maybe sometimes high temperature pre-treatment processes, and then we can go for the leaching operations with the help of the biohydrometallurgy. So hydrometallurgical reactions assisted with microbial activities are the part of the biohydrometallurgy. So these microbial activities can help in the bioflotation process, as we have already discussed. In some processes, in froth flotations, they are using some biocollectors or bioorganism as a frother or collectors or activators during the froth flotation processes to enhance or depress the material during the froth flotation. Then there are bio-oxidation processes like microbial catalyzed oxidation, especially for Fe2 positive and sulfur species. Then biocomplexation, they are using biocomplexation process for the generation of organic compounds that favorably complex with metal species. Then there is biosorption or accumulation process with the incorporation of metal species from solutions into biomass. So what is bioleaching? So bioleaching is generally microbially assisted leaching of certain minerals by a bio-oxidation or biocomplexation process. So bioleaching can be applied to various ore types through microbial generation of leach agents or organic acids, and cyanide bioproduction remains at laboratory states, and most R&Ds are focusing on biooxidation, which is only the bioleaching process to reach industrial implementation. Okay. So coming to the history of bioleaching or biooxidation processes, the first heap bioleaching was introduced in the 17th century in the Rio Tinto mine for the recovery of copper metal from the lean grade copper ore. So solubilization of metals associated to the sulfide matrix by bacteria, a natural phenomenon known and used since earliest antiquity from 17th century, which is known. So they have used bioleaching operations with the help of acid mine drainage and and metal recoveries, especially copper in the Rio Tinto mines. So coming to the bioleaching or biooxidation process, bioleaching is basically an established technology and an industrial reality for ore processing from lean grade ores, which generally used H2SO4 as an inorganic material, and bio microorganisms are used to enhance the recovery process during that whole leaching process. So these bio microorganisms can act as a we can say enhancer during this whole leaching operations by reducing or by oxidizing particular elements present inside that particular ore, and with the help of those redox reactions we can go for the selective leaching operations from the particular ore via these bioleaching operations. Okay, so this is for today, and thank you for joining this course. So maybe we will meet next year in the same course or maybe in some another course. Until then, goodbye.